Chapter 9, Section 1, The Nature of Waves. Okay, I had to go back and I forgot to turn my pen on here. So, waves. A wave is a repeating disturbance that transfers energy through matter or space. Here's the big thing right here. Transfers energy. Matter is not transferred, only energy. And this is through matter or space. Other examples, here's examples of different types of waves: ocean waves, sound waves, seismic waves, light waves, and of course there's different types of waves. All right. So in this picture right here, it's going to say waves and energy. And what's going on here? If I have a pebble and that pebble hits the water here, trying to draw a decent arrow. Okay. That pebble hits that water, then the energy, the kinetic energy of the pebble as it enters the water, it transfers that. When the pebble hits, it doesn't speed up, it slows down. And it slows down because it loses some energy here. And that energy, a rock or a pebble or anything, we know when we throw something in water that we get these waves, okay? It's the energy, kinetic energy. It hits and the energy is transferred into the water, and that energy shows up in the form of a wave, okay? Now, as the wave travels outwards from the impact point, the wave gets smaller just because the energy is being transferred to more matter. As that energy is transferred to more matter, the wave gets smaller. Remember, you cannot create or destroy energy, but it can change. So the kinetic energy of a rock hitting this water, the rock will slow down as it enters the water, and some of the energy is given off in waves. All right. Waves and matter. And this is the big one. Again, I'm going to go right down to this right here. Waves carry energy without transporting matter from place to place. Okay, so waves transfer that energy. They transfer energy. They do not transfer the matter. Those little particles stay where they're at. They vibrate back and forth, but all they do is carry the energy. Okay, so all waves, whether they are water waves, sound waves, light waves, or earthquake waves, have this property. They carry energy without transporting matter from place to place. And a wave only lasts as long as it has energy. Okay, when that energy dissipates or is transferred into another object, the wave will stop. Okay, so making waves. A wave will travel only as long as it has energy to carry it. When you drop a pebble in a pond, small waves form as shown in Figure 1. These waves carry energy. However, this energy is gradually transferred to the surrounding water and air. At the same time, the remaining energy in the wave spreads out as the waves spread out. As the energy spreads out and is transferred far away from the waves shrink and disappear. That's because they're going into more matter. Okay, it's being transferred into more matter. But here it is right here. And then it's going to talk about this. Whatever kind of energy you put into this wave, okay, if you put a lot of energy in, you're going to get a larger wave. If you put a small amount of energy in, you'll get a smaller wave here. Okay, so it depends on the energy. The more energy you put in, the more wave, the larger the wave. Now, you'll see here how this person is making a wave. The wave travels down the rope or the string, and it is transferred through the string. The energy that you put in is transferred through the string, or the rope in this case. Okay, so mechanical waves. Right? Making waves, and then mechanical waves. Sound waves travel through the air to reach your ears. Ocean waves travel through water to reach a shore. A medium is the matter through which a wave travels. I'm right here. A medium is the matter which a wave travels. The medium is what the energy travels through. Okay. Any wave that needs a medium is an mechanical wave. Okay, it's a mechanical wave. The reason I said electromagnetic is because electromagnetic waves, like the light from the sun, the heat from the sun, those are electromagnetic waves. They do not need a medium. The only type of waves that need a medium are mechanical waves. And there are two basic types of mechanical waves. There are transverse waves and a transverse wave. Now, I'm going to draw this here, and I'll explain this. This will make more sense to you in the next section, why I'm drawing this. This is called a rest point, and this is what an oscilloscope kind of looks like, and that's why I'm doing it like this. So let me change colors here and draw a transverse wave on here. Okay, here's a transverse wave. A transverse wave looks like this. Oop. These are transverse waves, okay? So water waves, transverse wave. In transverse waves, the energy moves at a right angle. So the energy here moves at a right angle. Boom. Okay. The energy moves at a right angle. It's going to move up like this and at a right angle through here. So my energy in a transverse wave travels in this direction. And it's talking about water waves. Water waves are a combination of a couple different types of waves. But anyway, here's my other type of wave. And it is a longitudinal wave. Longitudinal wave. So again, here, energy travels at right angles. It's going to move in this direction, and it also moves in this direction at a right angle. Okay, that energy is going to go like this. The more energy I put in it, boom, the bigger the wave is going to be, and that wave is going to travel in this direction. All right. On a longitudinal or compression wave, a lot of times you'll hear it called a compression wave, not a longitudinal wave. So it's two different types of waves. But again, we're going to draw our rest. Okay, there's our rest, and let's get a color here. I don't know. Let's do dark green. I like green. So let's check out green. A longitudinal wave moves back and forth along the same direction that waves travel. You can model longitudinal waves with a coiled spring toy like a slinky. But what we're going to do here, and we're going to go like this. We're going to try to do this. Oop. My hand got on the cord and it kind of messed things up there. So let's try this again. Okay, so you're going to have these areas that are spread out and areas that are bunched together. And the energy here in a longitudinal wave or compressional wave moves in this direction, okay? Matter in the medium moves back and forth along the same direction as the wave travels. You can model longitudinal waves with a coiled spring toy as shown in figure 5. Squeeze the several coils together, and you can see here, this is the way we draw a compressional wave compared to a transverse wave. Transverse waves are big and loopy, and compressional waves are all jammed up in there. Look like Charlie Brown's shirt. Okay. Sound waves are longitudinal waves. We'll talk more about that too. Okay. Seismic waves. Seismic waves are both. There's primary waves and there's secondary waves. So these primary waves and secondary waves, seismic waves are both. They're both longitudinal and transverse. Okay, so seismic waves are both longitudinal and transverse, and it's a combination of these that bust stuff up. You can imagine them moving back and forth and up and down. It busts everything up, and that's what seismic waves are. Okay, all right. So after we've gone through this, I want you to take a look at the notes, and they should help you with the homework.